And there we go. Okay. Let me move that out of my way. Now, before I get started, are there any of these review questions that gave you trouble we need to be sure and get to? Okay. So I'll just take the ones I've marked off and we'll roll with it. All right, number 1. Elements in group 1A and 7A, Roman numeral 7A of the periodic table possess respectively how many valence electrons? Okay, this is the old system of numbering the groups with the Roman numerals. And the Roman numeral tells you how many valence electrons there are, right? So it's 1 and 7. Yep, okay. That was simple enough. Yeah. How about 2? Formation of a positive ion is the result of an atom. What? How do we form an ion? Right? If you have so many protons, that means you have the same number of electrons if it's neutral. So the only way to form an ion with a neutral atom is to gain or lose electrons. Because if you mess with the protons, you got a different element. So the one that satisfies that is B. You lose 1 or more electrons to form a positive ion. So you have to lose electrons. All right, see here. So we can get 3 and 4 on there at a time. 3. How many total electrons are present in an N3- ion? Okay, well, we start with the neutrals. That's the way I do it. Start with neutrals, and we've got 7 protons, so we start off with 7 plus 3 is 10. Yeah, okay. Hope they become more challenging. 4. Element groups 2A and 7A form ions, expected to form ions with charges of. Okay. You have to think about where these are located. So you've got 1, you got 2, and then we skip the transition elements, and you got 3, 4, 5, 6, 7, and 8. Let's see, 7 and 8. These are the noble gases, right? So they're not going to form any ions.
I had to take a long way around.
Were you flooded?
No, it's raining, and parts of that hill is like so slick because so much water comes off the hill. So I took a long way around.
You're a hydroplane.
Yeah.
Be sure and sign in.
Okay. I was like, you were gonna think I'm not coming, but I'm coming.
No, Kinsley's on Zoom, and she sent me a message you were going to be a little late.
Oh, okay. Well, I stressed myself out.
We're doing review right now for the next exam.
Okay.
Do you guys need any documents? You probably got from last 2 weeks ago.
The review packet or whatever.
Yeah.
Just rolling.
Okay, so we're on 4, 2A and 7A. So we're looking at this group and this group. On this side, the metal, they form ions by losing their valence electrons. So if you got 1 or 2 valence electrons, it's going to lose both of them. So that means it would be a preferred 2+ charge. On this end, the 7s are very close to having an octet. So they form ions where you gain an electron. So we've got a +2 and a -1. would be their preferred ions. These are the halogens. These are the alkaline earths. Let's see, 5 and 6. Yeah, we can get those on there. Okay. The correct formula for the ionic compound that might be formed between sodium and arsenic. Okay. So which one comes first? The metal, right? Sodium comes first, and then arsenic. Okay. So this is going to be a type 1 compound because the metal comes from a group that only has one charge. It's always +1. Arsenic is a little different story. It's a nonmetal. It comes from the nitrogens. It's a nitrogen group. And when they form ionic compounds, they always have a 3- charge. Right? Nitrogen does, phosphorus does, arsenic, antimony, all those have 3- charge in this type of compound, ionics. So that means we need 3 sodiums to balance the charge. And that would be A, be the answer for that one. Let's see, 6. In which of the following pairs of compounds are both members of the pair ionic compounds? So the first thing you need for an ionic compound is metal and a nonmetal. So if we've got any non-metal compounds, throw that one out. Right, so the first one is phosphorus triiodide. Phosphorus and iodine are both nonmetals, so they can't be A. Nitrogen and chlorine, they're both nonmetals. Hydrogen and oxygen, lithium and fluorine, that's an ionic compound, but water's not. So lithium and iodine and nickel and oxygen, that has to be it, where you've got a metal and a nonmetal together. Before I get too deep into this, are there any of these problems that you guys had trouble with and we need to definitely get to? Okay, I'll just keep going with the highlighted ones. The correct name for the ionic compound, Fe2Se3. Okay, what type of compound is this? 1, 2, or 3? It could be a 1 or a 2, right? Metal, non-metal. So now we have to tiebreaker. Is it a 1 or a 2? It would have to be a 2 because iron is a transition metal. And it's not one of those that has a fixed charge like zinc, cadmium, or silver. Right? The rest of them are variable charge. So it's a type 2. That means we have to deduce what the charge is. So we got to go to selenium and say, all right, where's selenium? It's in oxygen's group. It's a chalcogen. So it's going to be a -2. Okay. So we have -6 total for the nonmetal. That means we have to have a +6 for the metal, and each one has to be a +3 to make that total charge. So now we name it iron, and then selenide, selenium, IDE on the end, and then the charge for iron, like that, iron 3 selenide. It looks like B. Okay. Okay, all right. Moving on. Which of the following statements about polyatomic ions is correct? Well, let's see, we've got to go through them. All have names which end in ATE. Is that true? No. First one that comes to mind for me is ammonium. Right? That's a polyatomic ion. All must contain one of the halogens. So this one's false. Do they all have to have halogens in them? I don't think so. Right? What about the cyanide ion? Right? That's a polyatomic. There are no halogens in that one. Now, a lot of them do have halogens. That's true, but not all of them. How about C? Negative ions are more common than positive ions. That is true. Right? The ammonium, that's the only positive one we've considered. Now, there's another one. When we get to, are we going to get to acids and bases? There's another one. The hydronium ion, it's also positive, but it's not in your list. And the reason it's not in your list is it doesn't form compounds like ammonium does. All carry a charge of 2. Nope. The charges are all over the place. All right, number 9 and 10. We get 9 and 10 together. All right. The formulas of the sulfate ion, the nitrate ion, and the phosphate ion are respectively. This one, all you have to do is look it up in the chart. All right, you're going to have that available for the exam. So sulfate is SO4 2-. Nitrate is NO3-. And phosphate is PO4 3-. So that would be D. And that's number 10. In which of the following pairs of ions are the 2 members of the pair isoelectronic? All right. So now we have to think about, do they have the same ionic structure? Let's see. Well, I guess we have to do them all at once, all of them. More than one correct response is possible, no correct response, so we got to do all 3 of them. C. Okay. Sulfur 2-. All right, so sulfur would be, if sulfur is a 2-, it gives it 2 extra electrons. It looks like argon, doesn't it? Just use your periodic table. The electronic structure should be like argon. There's sulfur, add 2 electrons, move 2 to the right, and you got argon. Okay, so it looks like argon. How about chlorine? Cl-. Cl-? Yeah, it looks like argon too. Right, so we got one there. How about B? Sodium and potassium. So we got sodium plus, potassium plus. Sodium, if you subtract an electron, it backs up 1. So sodium would be like neon. Potassium backs up 1, it looks like argon. So that can't be it. How about C? Aluminum and nitrogen. Aluminum is always a 3+. Nitrogen is, in this case, 3-. So if we back up 3 for aluminum, we go magnesium, sodium, neon. So that one looks like neon. How about nitrogen 3-? 3 to the right. Oxygen, fluorine, it looks like neon also. Okay, so we found our both A and C are isoelectronic. And we didn't actually have to sit down and draw out their electronic structure. Right, I'm sure you're sick of that. All right, 11. Let's see, which of the following elements would be expected to form a monatomic ion with a charge of +2? Monatomic, okay, so that's 1 atom. It has to have 2+. So it's going to be whatever the Z is, -2. Well, we have to look, where is it located? Let's take our examples here. A, B, C, D, and E. Oh, D and E are more than one or none. So first one's oxygen, sulfur, and magnesium. So we look, where are those located? Oxygen wants to gain 2 electrons. But look where it is. It's only 2 steps away from neon. So it's going to gain 2 electrons to get to neon. This one's going to be a 2-. Sulfur is in the same group. It wants to look like argon. Magnesium is an alkaline earth over there, the second column on the left. It gets to its noble gas configuration by losing 2 electrons. So as it backs up 2, it goes from magnesium to sodium to neon. So it does that by losing 2 electrons. And that's characteristic of that group. Beryllium, magnesium, calcium, strontium, barium, all those are 2+ charge. So C is the answer. All right, finally we get to skip one. How about 14 and 15? All right. Which of the following pairings of compound name and compound formula is incorrect? Okay. So we've got 3 to choose from, and then D and E are based on the first 3. So A says sodium oxide. And it tells us that this one is the correct formula. Is that true? What's the charge on oxygen when it's in an ionic compound? It's a 2-, isn't it? And sodium's in the first column, so it's a 1+. That's true. 2 pluses, 2 minuses. That one's good. How about B? Magnesium sulfide. And it says what? It says it's got 2 here and 1 there. All right, sulfur is the same as oxygen. It's in that same family, same group. So it's a 2-. Magnesium is an alkaline earth, it's 2+. Right? So that's wrong. You only need 1 of each. Yeah. And C, potassium chloride. Halogens are -1. Alkali metals are +1. That's good. So we got 2 that are right. More than 1 correct answer. Wait a minute. Oh, which one's incorrect? I gotta read my own question. Which one's incorrect? Yeah, it's this one. You know, that's confusing, isn't it? The question asks for the incorrect one, but one of the choices, D, says more than 1 correct response. So it could be B or D, couldn't it? All right, so if you run across one like that on the test, you could answer it either way and argue, I might count it wrong if you put D, but you can come back to me and get credit for it. Okay? For a question like that, that was poorly worded, to say the least. $15? Yep, 15. Well, this thing's giving out on me pretty quick. Which of the following compounds contain more than 10 atoms per formula unit? So we need 10+ atoms per unit, per formula. Right. So for this one, you've got to be able to write the compound. That's the only way you're going to get the answer for this one. So ammonium phosphate. There's ammonium, and there's phosphate. All right, ammonium has a +1 charge, phosphate's a 3-. They're both polyatomic ions. So that means we need a parentheses here. That's what you do with polyatomics. You don't change the subscripts. A parentheses with 3 of these positives balance those 3 negatives. So this one has, let's see, 3 + 12 is 15, right? 16, 20. So that has 20 atoms. So there's one. How about B? Aluminum carbonate. Aluminum. There's your carbonate with a 2- charge. Aluminum is 3+. So this one, the best way to handle this one is cross multiply. Take that 2 and put it over here. Take that 3 and put it over there. So now we have, let's see, 4 × 3 is 12, 13, 14. That one is more than 10. How about C? Iron 3 cyanide. This has a 3+ charge because it told you it did. Cyanide has a -1 because it's a polyatomic ion, and you just look it up on your chart. You see that's -1. So this one has 3. So this is 6 plus, that's only 7. Right, so these are the only 2 that have more than 10 atoms per unit. D is the answer. More than one correct response. Oh, lovely. Did we have any of these on the first test? Where you had to look at those 3 choices, 1, 2, and 3, say how many of them are correct?
Yeah.
Those really take up some time because you gotta look at each one individually. All right, let's get with it. Okay, is this true? The ions O2- and S2- are isoelectronic. O2- and S2-. Well, add 2 electrons to oxygen, you get neon. Add 2 to sulfur, you get argon. So that's false. How about 2? The symbol for an atom of X has lost 2 electrons. So if X loses 2 electrons, what is it going to be? Oops. It's going to be an excess of positive charge, isn't it? 2+, right? So that one says 2-. That one's wrong. How about 3? In all ionic compounds, the total charge of the ions present per formula unit must add up to 0. Yes, that is true. They have to add up to a neutral. The only time you have the charges add up to not different than a neutral, a positive or negative, is if it's a polyatomic ion. And then all the charges, well, actually, they're not charges. I'm getting too deep in the weeds, so let's just stop right here. That's true for all compounds. You want a neutral. Compounds are neutral by definition. Okay, 20. Calcium sulfide. Number 1, calcium sulfide is a compound in which both types of ions present have the same electronic configuration as the noble gas argon. All right. So 1, calcium sulfide. This is a 2- and this is a 2+, correct? That's an alkaline earth, 2+. This is a chalcogen, 2-. They always, that's it. So if we go calcium and back up 2, we get to argon. So that's the same configuration as argon. Sulfur, add 2, we get to argon. Right, that's true. That statement is true. They have the noble gas electron configuration. 2, the charge on the positive ions present in the compound Al2S3 is +3. On the positive ions. Yes. Great. So which one's positive? That one, the first one. It's a metal. And aluminum is always 3+. So that one's true. How about 3? The polyatomic ions ammonium and cyanide do not contain oxygen. So there's ammonium and there's cyanide. That's true. No oxygen there. So all 3 of them are true. All right, let's do these. We'll move something out of the way so I can see valence electrons. Okay. (21) For the electron configuration. 1s2, 2s2, 2p6, 3s2, and 3p5. Okay. Choose the appropriate number of valence electrons present for the response from the response list. All right. By definition, the valence electrons are those in the highest energy level. So that's this one right here. 7 valence electrons. That was easy. Let's see, we got another configuration. I'm going to leave those there so I don't have to write them again. Now we're going to go on out to 3p6. See, there, 3s2, 3p6, 4s2, 3d10, and 4p3. Okay. So what's the question? For this, choose the appropriate number of valence electrons present from the response list. Like I said before, you go to the highest energy level. And how do we know the energy level? It's the principal quantum number. It's this thing right here. So we have a 4 here. We have a 4 here. So that together is 5 valence electrons. All right. Let me see. I'm covering something up for the compound. Okay. 23. For the ion or element combination of M2 plus and X minus, M2 plus and X minus, okay. Choose the correct formula for the, oh, okay. Just balance the charges, right? So we need 2 minuses over here. That means MX2 should be the correct formula. (24). All right. Choose the correct formula for the compound formed when M, which is a group 3A. Where is group 3A? That's boron, aluminum, gallium, indium, tellurium. So what's the charge on that one? It would have to be a 3+, wouldn't it? Count over from the left. Skip over the transition metals. Right? Just stay in the representative elements. First column, second column, aluminum column. That's always 3+. And X, which is group 6A. X. So where's 6A? All right, well, look, got a shine on it there. 6A is the oxygen group, right? And that's always 2-, correct? Okay. So now all we have to do is balance charges. Put a 2 here and a 3 here, and you got it made. M2X3. Yep. There it is. And 25. Are any of these giving you trouble? Or are you kind of bored?
It's just been a long week.
Oh, okay. It'd be better if you're bored. That means you've got it pretty well in hand. You want to go on to something more exciting. Like chapter 7. 25. Choose a formula from the response list where a greater number of negative ions are present than positive ions. Okay, so if we've got these choices, goes all the way down to D. Okay, we've got potassium nitride, aluminum fluoride, calcium sulfate, and ammonium sulfide. Okay, we're comparing the number of ions. Positive ions, here we have 3. We have 3 here and 1, so that's not it. We have here 1 and 3. That's a good candidate. Oh, we're done. Because there are no oddballs in there like 2 of the above or none of the above. But there's only 1 here and 1 here because sulfate is a polyatomic, it's a single ion. And ammonium is 2 to 1. So there you go. B answers that question. (26) Choose the polyatomic ion that contains a total of 4 atoms. Okay, we're looking for 4 atoms in the polyatomic. B, C, and D, I think. Yeah. So hydroxide ions. What's a hydroxide? Right? That doesn't matter. That doesn't fit. How about ammonium ions? NH4 plus. Oh, that doesn't work either. How about nitrate? NO3 minus. Yep, that one works. And then sulfate's got too many. That's 5. 5, 5, and 2. This is the one that has 4 atoms in it. Let's see, 27 down here, like that. Choose the polyatomic ion that contains 1 hydrogen atom. Only 1 hydrogen atom. Right? That's a good candidate, hydroxide. Ammonium, we've had that one before. That's got 4 hydrogens in it. Nitrate's got none. And sulfate's got none. 2 minus, yeah, 2 minus. Okay, so there you go. Alrighty, 29. Which of the following molecular compounds would have a Lewis structure that contains 10 electron dots? 29. So remember how to draw a Lewis dot structure? If we got this one, where do you start first? You add up the valence electrons for everyone. This one has 1. Carbon has 4. Nitrogen has 5. So that's 10, right? 10 electrons? Oh, okay. We got our answer. If it's got 10 electron dots, that's it. We could go through the rest of them if you want to. Right, if we're pretending we're taking the test here, we want to do things as quickly as possible and get done with the torture. Okay, the total number of non-bonding electron pairs present in the Lewis structure for SiH4. All right. So what are non-bonding pairs? They're electrons that are not part of the bond, right? It's really simple. So silicon should have four electrons and 4 for the hydrogen. So we have 8 total. So we have a silicon in the middle. We have hydrogen, 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 hydrogen. So that's 2, 4, 6, 8. Used them all up. There are no non-bonding pairs in this molecule. They're all used up. So that's why the answer is 0. Kind of a trick question. Got you looking for non-bondings and they're none there. In which of the following molecules is a coordinate covalent bond present? Okay, this one is a little tricky. What is a coordinate covalent bond, first place? It's a covalent bond which is formed from 2 electrons or more, 2 electrons from only one of the bonding partners. So what we want to do is find a molecule that's perfectly happy without the extra bond. Okay, so if we were to look at A, HCN like that, actually it's got 2 there. So we need an octet here, octet there, and a duet there. All right. Would this one be happy like that? No, it wouldn't. Carbon usually bonds to 4. Or would it be happy like that? CN. Well, if it were CN, it would be probably this. Have the minus charge. So technically that's a candidate. We'll say questionable. How about this one? COO, like that. If you draw the Lewis dot structure, it'll look like that. Now there is carbon monoxide, right? But if carbon monoxide forms from electrons that are donated from both sides. And the same with this one. If we were to do that and then add the hydrogen, you get 1 electron from the hydrogen, 1 from the carbon, and that would be the bond. That's not a coordinate. This would not be a coordinate either. How about C? That's a perfectly happy molecule, just as it is. Right. So the last one is this one. Let's see, it's going to have like that. Notice the electronic structure. Here, it's perfectly happy just like that. Oxygen, if we draw the electronic structure for oxygen, how many electrons does it have? Valence electrons, right? It's in the 6th column. It has 2, 1, 2, right? It's happy like that. Well, it's reactive because it has unpaired electrons. But how many does it have after the bond? It's still got 6, right? So that's how you would deduce that the bonding pair came from nitrogen here to form that bond, because oxygen still has its 6 original electrons. That's the only way I can make sense of this one. Okay. Your other option is just memorize it. Okay. Another coordinate covalent bond question. These bonds differ from normal covalent bonds in that what? One atom supplies more electrons to the bond than the other atom. The ones we studied, one atom supplies all the electrons for the bonds. But there are coordinate covalent compounds where Both partners provide electrons unevenly. So A is the answer to 35. That's funny. The electrons of the bond move about in a coordinated pattern. Who made that one up? Atoms involved must always also possess non-bonding electron pairs. Sometimes they do, like the one that we just showed you, dinitrogen monoxide. That's laughing gas. Nitrous oxide. How about this one? 37. Which of the following statements concerning molecular polarity is correct? All right. All diatomic molecules are polar. Is that true? No, I'm thinking table salt. That's diatomic. Right? It's got now diatomic elements, yes, but not diatomic molecules. Oh, are polar, excuse me. No, not necessarily. Okay, I need to draw a distinction between molecules and ion pairs. Molecules are covalently bonded. So if you have, our example earlier was nitrogen, that's a covalent bond. They have to share electrons. They're both nonmetals. Water, that's a covalent compound. Right? But the diatomic covalence, that's nonpolar. Right? So it can't be polar. You just need one example to make that one false. So A is false. Not all. All linear triatomic molecules are nonpolar. Can you think of an example? That one's false. How about B? Linear triatomics. Well, this one is a triatomic and it's linear. Right? So that's nonpolar. But how about this one? The one we just looked at a few minutes ago. That's polar, right? Because oxygen is more electronegative than nitrogen. So it's going to be polar this way. Okay, so that's one example that makes this one false. How about C? What does C say? Triatomic molecules in which all bonds are polar must be polar. Triatomic molecules in which all bonds are polar. Oh, I showed you before, right? Carbon dioxide is a triatomic molecule. This bond is polar that way and it's polar this way for the other oxygen. But they cancel each other out, right? So C is false also. There are no correct answers there. They're all false. Let's see, 38, okay. We're doing on time. We're good. For which of the following pairs of compounds do both members of the pair have names that contain the prefix di? Both pairs of the compounds, do both members of the pair have names that contain the prefix di? Wait a minute, that's not right. Carbon dioxide, sulfur dichloride, potassium oxide, right? That wouldn't work. So A is false, obviously. Because for ionic compounds, you don't have mono, di, tri. That's only for the type 3 compounds. So this one is false. How about B? CO2 and N2O. Let's read that question again because it's confusing me. Which of the following pairs of compounds do both members of the pair have names that contain the prefix? Okay, so both pairs do have di in the names. This is dioxide and this is dinitrogen. Right, okay, so that one's true. Yeah, B is true. C can't be true. Hydrogen sulfide, well, technically dihydrogen sulfide. Dinitrogen trioxide for C. Well, okay. Typically, we say the name for this one is hydrogen sulfide. We don't say dihydrogen sulfide. And I'm not sure why. I think possibly because the electronegative difference between the two is such that this is named with the ionic convention. This is a +1, this is a -2. So that's why you don't have a di in this name. Oh goody, number 40. Okay, 40. First choice, once a coordinate covalent bond is formed, there is no way to distinguish it from any other covalent bond in a molecule. That's true. Once it forms, you can't prove that it formed from electrons from one side and not the other. Now, you may be able to deduce, like we did before, that it's probable that it was a coordinate covalent bond, but there's no way to prove it. So 1 is true. 2, the least electronegative elements are located to the far right in the periodic table. Is that true? No, they're to the left. Remember the trend is lower left to upper right. So the least electronegative would be on this side. So 2 is false. How about 3? The central concept of Vsepr theory, remember what that stands for? Valence shell electron pair repulsion. That gives us our geometry. The central concept of Vsepr theory is that the electron groups in the valence shell of a central atom in a molecule attract each other. I don't think so. Negatives attract? That was false. So there's only one right answer. C says there's only one statement that is true. 44, got another one. All right. An unpaired electron is present in the Lewis structure for the molecule NO. An unpaired electron in the Lewis structure of NO. All right, so we got to write the Lewis dot structure for NO. N has 5 and O has 6 electrons. So there's 11 electrons total. So NO, okay, -2 is 9. We've got 9 electrons left. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's see. 1, 2, 3, 4, 5, 6, 7. Okay. Now we have to decide how we're going to make an octet for nitrogen. We got 2, 4, 6. We need 2 more. We need another bond in here. So where are the electrons going to come from? Well, if we take one from this side and one from that side, then we can make another bond, assuming it's not a coordinate covalent. That means 2, 4, 6, 8 for oxygen, 2, 4, 6, 7. So nitrogen is deficient. Now, how do we know it's nitrogen and not oxygen that's deficient? We could have gone the other way, couldn't we? right? And made oxygen the deficient one. The general rule is the more electronegative one wins. It gets most of the electrons. So oxygen's going to have its octet and nitrogen's going to be deficient. But there it is. That's an unpaired electron. And what's this called? This is true. That's called a free radical. Unpaired electrons in a compound, in an ion, in a molecule of any kind means that it's a free radical, which means it's very reactive. So nitrogen monoxide is extremely reactive. This is the compound, nitric oxide they call it. This is the compound that's responsible, they say, for good blood pressure. Right? If you get that in your system, it'll cause your vessels to dilate and lower your blood pressure. Now, you don't get this in your diet. Right? If you take something like super beets, right? They're loaded with nitrates. And the nitrates go into your gut. And the microbes down there change the nitrates into nitric oxide. And that goes into your system and lowers your blood pressure. It works. I've used it just to see. It takes about 20 minutes to start feeling the effects, and measurable effects. And my blood pressure drops about 10 points. Okay, so, we didn't do the last one. So this one is true. 2 is true. Oh, no, 1 is true, excuse me. The molecule nitric oxide is naturally present in the human body. No, I don't think so. I think it's formed by the action of microbials in your gut. The acronym ORP stands for the odor replication process. Odor. Okay, so that tells me that they're saying that this one's true. It's naturally present in the body. Yeah, it is. It's just that the human body doesn't make it. We absorb it from our gut. And if we're going to have 2 of the 3 that are true, it would be these 2. I don't know where that question came from. Is that in one of your chapters in the book? Don't know. Okay. It's not that important.
I feel like the book, like, we haven't really had to use it because I feel like the PowerPoints have been helpful. Yeah, like.
Okay.
I feel like I haven't had that many questions for the PowerPoint that we do.
Yeah.
Explain it pretty well. Like, I feel like it breaks it down better than the books.
So you could probably do without the book, huh?
Yeah, honestly.
And save some money.
Yeah.
Yeah. Well. Okay, 45. Choose the correct number of shared electrons in the Lewis structure of water. Right? So we've done this one often enough. The number of shared electrons. Correct number of shared electrons. 2, 4. There should be 4 shared electrons, 2 bonds. 46. Characterize the bond that forms between carbon, and this is electronegativity, carbon and hydrogen, 2.1. So how do we characterize that bond? What's the difference between the 2? The difference is 0.4. So what does that make it? Well, it makes it a covalent bond. The difference isn't big enough to be ionic, right? We got to be over 1.2, I think. So it's covalent, but is it polar covalent or non-polar covalent? It's non-polar. Covalent. Oh, we got another one, 47. Okay, 47. Characterize the bond formed between lithium and oxygen. Lithium and oxygen. Oxygen is 3.5 and lithium is 1.0. So the difference is 2.5. That's definitely ionic. Okay. And you can also say, look at how far apart they are on the periodic table. Oxygen's way over to the right, lithium's way over to the left. That's got to be an ionic bond, whether you know the numbers or not. (49). Now we're going to do some geometry. Compounds with trigonal pyramidal geometry. All right, so we have a trigonal pyramidal. This is the molecular geometry, not the ionic. Electronic. Do the electronic first, and then you cover up the lone pairs and find out what your structure is from there. All right, what's HOH? That's water, right? So what's the geometry of water? That's bent. Or your book might call it angular. How about the next one? NO? With all the other electrons around it. That's linear. Okay. How about C? Let's see. P, H, 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 and a lone pair there. So if we got at this one by going through the electronic geometry, what's the electronic geometry here? Tetrahedral. So if you got a tetrahedral structure here, right, like that, like that, like that, and we've got phosphorus in the middle, and we've got a hydrogen back here, a hydrogen here, and a hydrogen here, and then the lone pairs are up here, that's your tetrahedron right there. Okay? But if we cover up the lone pair, what do we have? We have phosphorus at the apex and the hydrogens at the corners of a triangle. That's a trigonal pyramid. So this is correct. We found our answer. D, just for argument's sake, what is D? Well, that's methane. That's going to be a tetrahedron.
I do not miss that stuff.
You don't miss it.
No, because I took another chemistry class before I came to do this one.
Oh.
And we focused a lot on that. But it was just like, it wasn't that he was a bad teacher, it was just so confusing. And I was like,
Well, do you know what the regular shapes are? If you have two groups around the central atom, it's going to be linear.
okay.
Right? They try to get as far apart from each other as possible. So two groups means linear. Now this is electronic structure. Now you have to do that first. If you have three groups, it's trigonal planar, which is another word for an isosceles triangle. Okay. If it's four, you have tetrahedral, like this one.
Well, that might be why I was
And if you have five,
like that, it doesn't seem that bad.
if you have five, then you got three here, and then you got one here and one here. But you got your triangle, and then you got one up here and one down here. So there's five of them. 1, 2, 3, 4, 5. And that's a trigonal bipyramid. Okay. And then the last one we did was you just change this one to a square in the center. And that gives you your 6 groups. And that one's an octahedron. That means it has 8 sides. So if you look up here like this, and you look going down on this side of the square, there's a side, there's a side, there's a side, and there's a side. That's 4 on top and 4 on the bottom. So it's an octahedron. Now, once you've got the electronic structure, then you have to decide what's the molecular structure by positioning your lone pairs. If you have any lone pairs like this one, right, it goes up here, but if you cover it up, what's left? That's the sequence of the procedures to get your answers. There are a whole lot more than this, but that's far enough. Right. I don't know if your other teacher went beyond that though.
You also have to like name like with methane, like then whatever else like could go with it. I can't remember what all it's called.
You're talking about substitutions?
Maybe.
Like instead of 4 hydrogens, you stick something else in there for one of the hydrogens or 2 of the hydrogens?
No, it was like I have my notes somewhere. I kept them just in case this class is going to involve it, so I can try to.
Yeah, we sort of, yeah.
Well, hopefully it won't be as bad.
Now, was that course you were in like this one semester and you're done?
Yeah, well, I think it was at Mount West, they labeled it as 205 only, but it wasn't like organic. It was like I've seen some stuff that we've done in here, we've done in the other class, but it wasn't like a lot of it. I think
Was it a GOB, general organic biochemical?
general. It was general.
General chemistry? Okay, general chemistry usually has 2 semesters.
Oh, really? See, I think we went 5 days a week for that, or 4 days a week for that one.
Okay.
So maybe that's why. I think it was like, or Mondays, Wednesdays, and then
Okay, just for an hour at a time.
no.
Was it in the summer?
No. Yeah, I think it was 2 hours or 3 hours.
My goodness. How much credit did you get for it?
It was a 4.
Was there a lab involved?
No,
Oh,
it was very rough though. Like I just kept doing it.
Mount West.
Yeah. It was because I work in not Logan, Huntington. So I was like trying to do like everything together.
Uh-huh.
But then I was like, well, I mean, it's not much closer, but if like the weather's not bad, then I can go to probably be here in 30 minutes.
Mm-hmm.
But if not like then it's still an hour, but it's not an hour and 30 minutes. Plus like if I run into the traffic that way, like it can turn into almost 2 hours.
Yeah.
So I was like, well, that's pointless, like for me to do that when I can just come here and it'd be way faster.
Yeah.
Now, the nursing program, the only reason I done it in Huntington was because you can sign a contract and have the student paid.
Oh,
So, I mean, it's 5 years, but I mean, that's 5 years I don't have to be in debt. But now if you fell out, then you have to pay all of it back. So, I mean.
that's what you're in now?
I started that in August as long as I pass this class.
Okay.
So no pressure for me.
51.
I literally have all the classes besides nutrition, and I'm in that also this semester.
Uh-huh.
And then I have micro left after these 2. I wanted to do micro here, but they don't have a lab part, so it doesn't transfer.
I see.
So then I do have to go back.
With all these microscopes and they don't have a lab?
That's what I said.
Yeah.
I was like, and plus it's online, so they were like, that won't count.
Oh, no.
So of course I have to go back that way, but it's fine. Like, cause I'll already be down that way, so it's not like I'm
Yeah.
driving for no reason.
I thought micro was a fun class.
I think it gets confusing, but I struggled with anatomy and stuff, but Ellis was my anatomy teacher, and I really liked having him.
Uh-huh.
He was a really good teacher.
Select the correct number of atoms in 1 molecule of dichlorine monoxide. Dichlorine monoxide. So it has 3 atoms, right? That's pretty easy. This is a type 3 compound, non-metal, so we have to say how many there are. That's the nice thing. There's no guesswork there. It tells you how many. 53. Another one. The correct number of atoms in one molecule of hydrazine. Ooh, what's hydrazine? Hydrazine. I think it's that. And then see, 2, 4, 2, 4, 3, 7. No, it's not right. Maybe it's like this. I think this is hydrazine. I'm gonna look it up. I should know that. You might even find it in your book. But it's worth the time. I know it's a very reactive compound. It was used as a fuel by the Nazis in their little rocket plane. Killed a bunch of people too. It was very difficult to handle. Hydrazine. Oh, I missed it. It's like this. There we go. That's hydrazine. Come on. I thought it was going to give me a formula. I mean, a structure. Well, that would be 2468, 2468. Okay. It has 2, 4, 6 atoms in it. What's the formula mass for ammonium phosphite? There's ammonium. And there's the phosphite is PO3, but it's still a 3 minus. It's still a 3 minus charge, so we have 3 of these. Okay, so what's the formula? What's the formula mass for that? Well, let's see, we have 3 nitrogens. We have 12 hydrogens. Okay, that takes care of that. 1 phosphorus, which is, I'm getting a glare, 30.97. And 3 oxygens. Just add them together. And it should be grams per mole, right? For that formula. Now, why do we say formula mass and not molecular weight or molecular mass? Because this is an ionic compound, right? And when they're all together, they're just those ions interacting with each other. This is the simplest whole number ratio of the cations and the anions in that solid. "56. What's that all about? Which of the following statements concerning Avogadro's number is correct? It has the value of 6.02 times 10 to the minus 23rd. I don't think so. It needs to be a positive 23. It's a huge number. So A is false. B, it denotes the number of molecules in 1 mole of any molecular substance. This is true. That is true. B is true. We got any others? No, we found the right answer. It is the mass in grams of 1 mole of any substance. Mass in grams of 1 mole of any substance. Denotes the number of atoms in 1 mole of any substance. No, not necessarily. If we have a mole of that previous compound, it'll be many more moles. It's the mass in grams of 1 mole of any substance. You know, the way that's worded, C could be an answer too. Couldn't it? Can you think of a reason why C wouldn't be a good answer too? It is the number of molecules in 1 mole of any molecular substance. That's true. Okay, so in this case, pick the best answer. And B is a better answer than C because C is kind of nebulous. That's the best I can do for that one. Avogadro's number of sulfur atoms would have a mass of, well, sulfur is 32 grams. We just look on the chart. 32 grams per mole, 57. Sulfur, 32 grams per mole. That's its molar mass. That was easy. Let's see, let's do this one. 58. Which of the following samples has the largest mass in grams? Oh, so we have to compare them. All right. Henry Ford time. Just go down to D. Yes, just to D. Okay, 5 moles of carbon dioxide. 5 moles of CO2. 6 moles. 6 moles of cyanide. 7 moles of water. And 8 moles of hydrogen. Okay, so we need conversion factors for all these. So if we're going to find out how many grams, I think I need a new marker. We need the molar mass. So what's the molar mass of carbon dioxide? Well, 2 oxygens is 32 plus 12. So I'm gonna abbreviate because I think they're far enough apart. So that'd be 44, right? 44 grams per mole. Cyanide. So that's 12 and 14, which is 26. 26 grams per mole. Water is 18 grams per mole. And hydrogen is 2 grams per mole. So 2 times 8 is 16 grams. 18 times 7 is what? 126 grams. Did I do that right? I think I did. 26 times 6. 156 grams. And 5 times 44. Let's see. 22 and 20 is 220. There you go. Carbon dioxide has the greatest mass of those select. So if you set it up like this, right, you're going to do the same calculation for each one with just different numbers here. That's why I call it Henry Ford. I set up an assembly line. Let's see, can I get all of them in there? Yeah, there we go. How many atoms are present in 10.4 grams of germanium? 59. 10.4 grams of germanium. All right. This just sets up the calculation. So how many atoms are there? First, we got to convert to moles, right? So we need grams on the bottom, moles on the top. I got to look up germanium. I don't have that one memorized. 72.59. 72.59. That makes 1 mole. And then we convert the moles to the number of atoms. Right? Cancel the moles, and we have atoms. And that's Avogadro's number. Okay. So which one of these satisfies that one? Looks like C. C would be the correct calculation to determine the number of atoms of germanium in 10.4 grams. Let's see, 61. Oh, we're going to balance an equation now? Which set of coefficients would balance this equation? C4H10. C4H10 plus oxygen. Yep, we're going to burn butane.
Oh, that was one of them
One of them what?
that you put in the group, like in the other class.
Yeah.
Like there would be figures and we would have to put like butane, methane,
Oh, you'd have to name the organic compounds?
yeah, and the little tiny picture figure.
Oh.
And like, I don't know.
So you did have some organic chemistry in there.
I guess.
Yeah.
But I don't know. I don't know. I'm struggling so bad with that chemistry class.
That's methane.
Well, and
That's
then, like,
ethane. Right? Remember ethane?
yeah, ethane. And
H8.
something about,
This is propane.
yeah, I remember that.
Ethane.
So we would put those in like the figures like we just done,
Oh, you'd have to draw the structures.
yes, and then we would like list what was in them. I
Okay.
mean, it doesn't sound hard now, but it was back then.
Okay.
That's it. I'm so glad it took me forever to remember that.
So now we're just going to balance the equation. So this is the combustion of butane, right? We want to set up our budget: carbon, hydrogen, oxygen. So we got 4 carbons here, and we have 10 hydrogens and 2 oxygens. On this side, we have 1 carbon, hydrogens, 2 hydrogens, and 3 oxygens. So where do we start? If you don't have any intuition about it, just start at the top. 4 carbons there, we need 4 carbons here. That changes the oxygens. Have 8 plus 1 is 9 oxygens now. Okay, now we come down to hydrogens. So we got 10 hydrogens here, we need 10 on this side. So there's a 5 coefficient there. 10. Now we have 5 oxygens plus 8 is 13. Okay, and remember the trick. We're holding this element to last, because if you put a coefficient in front of that element, it only changes that one element, doesn't change anybody else. All right, so how do we get 13 oxygens out of this one? Right, that's a prime number, that's a prime number. Never the twain shall meet. Use a fraction. 13 halves makes 13, right? Now we just need to get rid of the fraction. All right, so we're going to multiply the whole thing through. These ratios, 1, 13 halves, 4, and 5, those ratios now are fixed for our balanced equation. Our equation is balanced and we can see it from the budget. But we want to keep that ratio. And now if we multiply those coefficients by the same number, we can get rid of that fraction. So 2 times 13 halves is 13. And then we need a 2 here because it's 2 times 1, and then 8 here, and then 10 here. So we use that 2. It's 2, 13, 8, and 10. That's D. Okay, 62. This one's starting to run out of steam too. Potassium forms an oxide with the formula K2O. That's true. +1 - 2. There you go. What is the coefficient of oxygen in the balanced equation of the reaction of potassium with oxygen to form the oxide? So we're forming this one by the reaction of potassium metal and oxygen gas. You have to know that that's diatomic, otherwise you won't write the formula correctly. Remember the diatomics? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All those are diatomic elements. So now that we've written that correctly, and it's going to produce this, then we can balance it, right? We need 2 oxygens on this side, right? 2 oxygens. Now we got 4 potassiums. So there you go. So what's the coefficient of oxygen? 1. Don't forget that there's a 1 here. We don't write it, but it's there. Oh, another one. Okay, let's see, 64. Another unit conversion. Which of the following is correct setup for the problem? How many grams of water will be produced from 2.1 moles of oxygen and an excess of hydrogen sulfide according to this reaction? Oh, they give us the balanced equation. That's good. 2 hydrogen sulfide plus 3 oxygens yields 2.1. Yields 2 waters plus 2 sulfur dioxide. Okay. Now, what are we given? 2.1 moles of oxygen and excess hydrogen sulfide? Yes. Okay. So we can use up all the oxygen and produce water. They want to know how many grams of water. Okay, so how do you do that? Well, we've already got moles here, so we can move anywhere in this equation we want to. But we need to change moles of oxygen to moles of water first. All right, so what's our conversion factor? 2.1 moles of oxygen. We're going to convert to moles of water. So what's the ratio? 2 waters for every 3 oxygens. Okay. Now we've got moles of water. We just need to convert moles of water to grams of water. And that's 18 or 18.02 technically. And that takes care of that. Okay, so that's our setup. So which one matches that one? Let's see, here. C. C is the best answer for that one. Got a half hour to go. I think I can make it. Get that down there. I need another marker though. This thing is pooping out on me. Maybe this one's relaxed long enough to feel right. 65. The atomic masses of helium and beryllium are 4 and 9.01 respectively. So helium is 4 atomic mass units and beryllium is 9.01 atomic mass units. Okay. Which of the following statements are true? A mole of beryllium contains more atoms than a mole of helium. Is that true? What was that poet? Was it Gloria Stein? A rose is a rose is a rose. A mole is a mole is a mole. Right? A mole of that is the same as a mole of that because it's the numbers of. So A is false. A mole of helium is heavier than a mole of beryllium. It's the other way around. If you have the same number of atoms, but these atoms weigh more, then this one's going to be heavier. So B is false also. How about C? A mole of beryllium contains the same number of atoms as a mole. That's true. Yep. So only one of them is true. C. Okay, we'll skip a few. Oh boy, you get one of these again. Why did I pick these? Let's see. Number one statement. 2.0 moles of NO contains the same number of oxygen atoms as 1 mole of CO2. Okay, 2 moles of NO, 2 moles of NO. How many oxygen atoms is that? It's 2 moles of oxygen. And 1 mole of CO2, 1 mole of CO2. So 2 for each 1 mole of carbon dioxide, we have 2 oxygens. So that's true. Yeah, this one's true. How about 2? The coefficients in a balanced equation give the fixed molar ratios between reactants and products. That's true. That ratio, once you balance the equation, the coefficients tell you the ratio of reactants to each other and to products. How about 3? Avogadro's number is an experimentally determined quantity. Yes, just a simple statement. It is experimentally determined. If you know you have a mole and you can weigh it, a mole of atoms, you can weigh it. Well, it's more complicated than that. Let's take it at face value. That is true. It is experimentally determined, and the value for the Avogadro's number, the value of the mole, changes from year to year as we refine our techniques. But for our purposes, 6.022, that's good enough from now till eternity, because the differences they find are way out here in these decimal points. So all 3 of them are true for 70. $75. Contrast the magnitudes to 3 significant figures. Roman numeral 1. Moles in 28 grams of dinitrogen. 28 grams of dinitrogen. That's 1 mole because each nitrogen is 14.01. So 28 grams would be 1 mole. Roman numeral 2. Moles and 28 grams of carbon monoxide. 28 grams of carbon monoxide. So if this one is 28 grams, what's carbon monoxide? Well, it's 12 plus 16, right? That's 1 mole also. Right? 28. 28 grams. We have a 3? No, we don't. So 1 is equal to 2. Yeah, 1 is equal to 2. That's B. That was 75, 76, and 77. Let me see what I'm hiding over here. Molecules in. Let's put it there like that. 76. Contrast the magnitudes to 3 significant figure. Okay. This one's like the last one we did. The first part, the Roman numeral, is 28 grams of dinitrogen, which is 1 mole. We did that one already. How about 2? 28 grams of O2. 28 grams of O2. So the molar mass of O2 is 32 grams per mole. So this is going to be less than a mole. We don't have enough to make a mole. So this one is greater than that one. 1 is greater than 2. $77. Balance equation. Yeah, balance this equation. So we got methane yields what? C3H8, C3H8, propane plus hydrogen. So we need to set up a budget for this one. Probably be safer, wouldn't it? Just carbon and hydrogen. So we got 1 carbon and 4 hydrogens here. 3 carbons and 8, 9, 10 hydrogens. So I need 3 carbons over here, right? That makes 12. Yeah. 12 hydrogens. Now, how am I going to get 12 out of this one? Oh, I need 4 plus 8 is 12, so I need 2 here. Right? So 4 plus 8 is 12. So it's 3, 1, and 2. Okay? Y'all comfortable with balancing equations? Okay, good. Let's see, 79. Using the balanced equation for the combustion of ethane, how many molecules of O2, that react with 2 molecules? There's something wrong with that. The English is wrong in that sentence. Grammar's bad. How many molecules of O2 react with 2 molecules of C2H6? Oh, 7, right? That's just the coefficients. I was making it harder than it had to be. I didn't even write that one on the board. What's the molecular geometry of H2S? H2S. Well, if we go to the trouble, there are 2 valence electrons here and sulfur is 6. So that's 8 electrons. So we have a sulfur, we have a hydrogen and a hydrogen, right? That's 2, 4. That means we have 4 electrons left. Can't put any on the hydrogen, so we got to go in. 2, 4. Okay, we have 4 groups around the central atom. That means tetrahedral. Let's see. There's sulfur, and we have a tetrahedron here. There. We have a hydrogen here, a lone pair in the back, and a lone pair up here. So when you cover up those lone pairs, what are you left with? You're left with a bent molecule, aren't you? So it would look like this. Actually, it looks like water. It's a bent molecule, angular. Oh, is that it? It says there's another 15 of 16 pages, but it won't scroll any further. Must have deleted the last page. Didn't have any data on it. Okay. That's all for the review, unless you have questions and want to hammer on any particular problem.
Wait. Okay.
Okay.
Okay, so I like whenever you go over the ones like why it's true and false.
Oh,
I know that's awful, but it makes me understand why that's the right answer and the wrong answer.
the ones that have the like the three choices.
Yes. And like one's
Okay.
true, one's false.
Okay. We can find some more if you want.
Okay, well, hang on.
Okay.
41.
Okay.
It's just when I'm studying, I'm like, okay, why are these right? Why are these wrong?
Okay. Sure. There we go. We'll do 41. Okay. One, the predicted formula of the simplest molecular compound formed between nitrogen and fluorine is NF2. NF2. Well, you know,
Which that would be simple, but.
that one's not really simple. These are both nonmetals, so we can't use charge balance. So that could be true. So we'll put that one question for now. The majority of compounds containing covalent bonds rather than ionic bonds. Majority of compounds. Okay. If you look at it, from the perspective of organic chemistry, which is they're all covalent compounds, or most of them are, that the industry has produced massive numbers of organic compounds compared to inorganics. Inorganics are limited by charges, but organic compounds are not, and covalent compounds are not. Right? They can share electrons willy-nilly.
So it's false.
The majority of compounds contain covalent bonds rather than ionic. That's true.
Oh.
2 is true. Yeah. The majority do contain covalent bonds. 3, in Vsepr theory, double bonds exert double the influence of single bonds in determining molecular geometry. No. You treat them as equal groups. I know that doesn't make sense, because you would think with bonds formed from 4 electrons versus ones formed from 2 electrons would have more repulsive force. And that may be true in reality, but the theory says that you treat them alike. So that's the key here. So 3 is false. And that leaves 2 as possibly the only one. Only 1 is true. Yeah. I think what we're looking for here is maybe, I don't know what to say about this one, because these covalent compounds can run the whole gamut. It's like if you go from nitrogen, you can have nitrogen like that, or like that, or like that. You know, it's just whatever the sharing does. So 1 is so iffy. I think that's why we're calling it false. Have any others? That's who we did that one. Yeah, we did that one and that one. Oh, there's one. 18. The number of valence electrons possessed by an atom can never exceed 4. No, you can have 8, right? You can have 2 from the s orbitals and 6 from the p orbitals, right? So 1 is false. All you have to do is find one example and it turns that one false. Binary ionic compounds containing 2 nonmetals do not occur. That's about as false as it can be. The name of the ionic compound CH203. All right, so copper is one of those that can have 1 of 2 different charges. So if it's this one, sulfur is a 2 minus. This has to be a 2 plus total. That means this is a 1 plus. So it's copper 1 sulfide. Copper 1 sulfide. Is that what it says? No, it says copper 2. So that's false. Only one statement true. Two nonmetals. Oh, binary ionic compounds containing 2 nonmetals do not occur. Containing 2 nonmetals. I think they're all false. They're saying one of the statements is true. Oh, no, that's right. I think they're all false. So I think that's an error. That should be none of them are true.
Okay, so that one won't be on the test.
No. No, I won't expect that one to be on the test. That's a bad question.
Well, don't you forget, okay? Don't you forget.
All right, now I'm 70 years old. I have a right to forget some things. No.
Remember, you said.
Okay, remind me if I do. Okay. There's another one. You want to try that one?
Yeah.
We got time.
And then after that, can we skip to 42 after 17?
Okay.
Just because it talks about stuff.
Okay, number 1. If an atom loses 1 or more electrons, it becomes negatively charged. That's false. If it loses electrons, it's going to be positive charge. Number 2, nitrogen, a group 5A element. Is that true? Yes, nitrogen's a 5A, possesses 5 valence electrons. That is true. Polyatomic ions are generally not very stable and usually lose their identity during chemical reactions. That is false. Polyatomic ions are very stable. They're stable. Yes, there's only one statement true. Polyatomic ions are actually covalently bound associations of atoms that have a charge distributed over the whole group. And they find themselves in ionic compounds, but the polyatomic itself is a covalently bound assembly. And they're very stable. 42, you say?
Yeah.
Okay.
Well, I guess I'll take that back because all 3 are correct, but I didn't know that before I asked.
Okay. Both tetrahedral and trigonal pyramidal molecules have 4 Vsepr electron groups about the central atom. So if it's tetrahedral molecule, we have a form like this, right? Something there, and there. If they're each occupied by an atom, It's a tetrahedral molecular structure. But if one of them is a lone pair, then this in the center forms a trigonal pyramid. So that means they do have 4 electron groups around that central atom. That gives them the tetrahedral structure, the electronic structure. So yeah, 1 is true. The greater the electronegativity difference between 2 bonded atoms, oh, I'm overlapping a little bit, the greater the polarity of the bond between the 2 atoms. That's true. Differences in electronegativity assign polarity to a bond. And 3, a double covalent bond between 2 atoms is approximately twice as strong as a single covalent bond between the same 2 atoms. The qualifier there is approximately. Yeah, it's approximately twice as strong, but not exactly twice as strong. Okay. That's the way you get around that one. So with that wording, 3 would be true. Approximately twice as strong.